Okay. So let's talk about how to actually build PDAs. We kind of built up this. I gave you this inclination about PDAs, about how they got built up, and that they needed to be non-deterministic finite automata combined with the stack. But we never actually went through, we started just barely going through and building PDAs. Did we actually ever build one? I think we built one with parentheses matching. So let's go through that again, because I think that's an example that's worthwhile for going back. So the parentheses matching example has left and right parentheses, and we want to be able to match the same number on either end. And so what we do is we start off, and we have our start state, and the first thing we do is we have an epsilon, and then we push on we examine the top of the stack, and in this case we don't really care if anything's on the stack, and we assume it's going to be empty at this point. So we have an epsilon there as well. And then this will push onto the stack some symbol that denotes we are at the bottom of the stack. And this is actually a recurring theme when we have to start talking about memory, and something you see when we go to Turing machines as well, which is that we'll actually put other markers in a Turing machine to denote the beginning of an infinitely long tape, because you have to denote you have a tape that's basically identical. The only time you know where you start is at the start. So typically the first thing you do is mark in some way the very beginning, so that way you know what it is for future reference. And so that's what happens here, is we put some symbol on there. Now I put a smiley face last time, but traditionally it's a $, and I don't know why it's traditionally a $. I think because it's the key on the keyboard. People are like, well, I don't know, we'll put a $sign there. So once you are at the $sign, the next thing you need to do is you need to check to see, is there a left parentheses? And so we have a connection here where we say, is there a left parentheses? We don't really care about the top of the stack because we're not trying to pop anything off the stack. We're just trying to make the stack itself. And then we push onto the stack some variable, which I called Q. Now we could call that whatever we wanted to. The only thing that's going to matter is that it matches something later on down the line. So from there, we get to another state, and now we're in the start where we keep on asking ourselves again and again and again and again, do we see a left parentheses? We don't care about the top of the stack. And then we push on a symbol Q. Eventually, we'll see a right parentheses. Now, we only want to go down this transition if we both see a right parentheses and we see a Q on the top of the stack. We will then pop off the Q and replace it with an epsilon. Now, when we pop off the Q and replace it with an epsilon, this is literally just removing one element from the stack. And then from there, we now keep on self-looping, removing all the right parentheses. Eventually what will happen is we will at some point get down to nothing on the input. We don't care about the input in this case. But we will see on the top of the stack the $sign. And then we will push on there an epsilon. Now in theory we could push anything on there, but by tradition, when you enter the accept state, it's always good practice to make sure your stack is empty. You don't have to, that's not a requirement of PDAs, but that's sort of good housekeeping. And then that takes you to an accept state. Moreover, if we're allowing m to be equal to 0, so if m can be greater than or equal to 0, then we also want to make that an accept state as well. Because it's possible you have nothing, so you start off accepting. So one of the things I really want to hit home is that when we see an epsilon, in order to take a transition, we have to match both the top of the stack and the current input. So when we have epsilon, epsilon, those are two wild cards. We can take that transition free of charge. Now taking the transition will always can have the consequence of pushing something onto the stack. If we want to make a truly free transition, we can do that by having epsilon, epsilon, epsilon. That can be done free of charge, and it will not push anything onto the stack. This transition can always be taken, but it has a consequence of pushing something onto the stack. This transition can only be taken if we see a left parentheses, regardless of whether it's the top of the stack. But it has a side effect of pushing Q onto the stack. Here, this one can always be taken. This can be taken only if we see a right parentheses as our current character, and a Q is the current top of our stack. It will always, and one thing to note about these two is those two terms always consume the character they observe. So if you see both a right and a Q, you consume both of them. Now, you never put things back onto your input. You just move on to the next one, and that's how you consume it, is you move on to the next phase of your input, and that makes sense. With a stack, you consume it, but you have the possibility of replacing it with something. If you replace it with epsilon, then it's a pure pop. If I were to put another variable on there, it would actually just replace it with something else. Now, I don't replace it with anything here, but I could. That's a perfectly legitimate thing for me to do, to pop Q off and put a Z variable on instead. And we'll see a case where that happens very soon. Any questions about that? Okay, so I've shown you this sort of general process of how to build of what a PDA looks like, but I haven't shown you a formalization of how to build it. And because this is computer science, we always like having algorithms for doing things, rather than being like, I don't know, just look at it and see what the answer is. That's for mathy people. Anyone who's taking calc and goes through the litany of tricks that you learn in Calc 1. It's like, why does it work? I don't know. Just pick the right trick and follow it. I'm recording that. Take that, Jay Lee. I'm sure Jay Lee is going to be watching my videos for this class. So I want to talk about the formal process for turning a grammar, not necessarily a language itself, but turning a grammar into a PDA. So let's write up the grammar. We're going to do two example grammars. I'm going to show you how we work through them. We'll start off with the simple one because parentheses matching, again, we come back to this again and again and again and again. You talk about things to know for the test. Pretty much know a lot about parentheses matching when it comes down to PDAs. You need to be able to recognize parentheses matching when it's directly shown as parentheses matching or when it's secretly hidden by doing clever things like A to the M, B to the M. Or even more sneaky, A to the M, B to the 2M. So clever ways of doing parentheses matching and sneakily hiding them in there. The grammars for these are all virtually identical, but these are good things to know how to do. So let's talk about the grammar for parentheses M and parentheses M.
So by parentheses matching, you mean, or in that context, you're referring to it as having two inputs and having a proportional number of them in order?
Not a proportional number, an exact number.
I mean, exact based on proportion, or exact and derived from a proportion, because you've got M and N. And
no, it's M.
Oh. Well, but you did have A
to the M, B to the M. Yes, yes. In that case, it was proportional.
Yeah.
But this is exact.
Okay.
It is proportional. The proportion is 1. So let's start off. We have a start variable S, and S will go to two things. It'll go to Q or epsilon. Q will go to left parentheses, right parentheses, or it'll go to left parentheses, Q, right parentheses. Everyone good with that? So, step 1 for building a context-free grammar. Oh, this should show up so much prettier. They're so nice on here. Oh well. We build three primary states. So, state 1 is our start state, which we will creatively label Q start. State 2 is going to be our loop state. Loop is really a misnomer because we're doing recursion here, but we call it loop because we're silly like that. Computer science humor. We're looping when we're actually doing recursion. And then we have a final state, except. Now I want to point out that this methodology for building them is only one of several methods. This will produce a PDA, but multiple PDAs exist which can recognize the same language. So the next step is we add some intermediate steps to here. We add this sort of one state which exists solely to push on the start and end symbol of the stack. And so we're going to push on the epsilon. And then we come from our loop state to our except state when we see that symbol. So epsilon, $, epsilon. We also, from the state to our loop state, we push on the start variable. Now it happens here, the start variable is s. Hey, how convenient for us. But it could be whatever the start variable is labeled as in your grammar. That would be what you push on. So, epsilon, epsilon, push on start. Okay? Now what we do is for our loop state, we add self loops that read off of the tape of one of the terminals and read off the stack a terminal and push on an epsilon. And we have one of these for every terminal. So we have two terminals here. And so we have left, left, epsilon, and then we have another self loop, right, right, epsilon. You'll see why we do this in a few minutes. Okay. Everyone ready? So the next thing we need to do is we need to add intermediate states for every rule change. These states all have the case of examining epsilon on the input, the variable on the stack, and pushing on in reverse order the rule. So we will have, and let me do the simple ones first. So we have here one rule, S goes to Q. So what we will do in there is we'll add a loop here. Now there's only one rule, so we don't need to add an intermediate state for this to work. And this rule will say read epsilon off the tape, read S off the stack, and push on the variable Q. We have another one here, read epsilon off the stack, off the tape, S off the stack, and push on an epsilon. The reason why we push on an epsilon there is because we actually have that. So you have one of those loops for every rule. Now let's get to the Qs, because these become a little bit more interesting. For Q, we read an epsilon off the input, we read a Q off the top of the stack, and then we push on, in reverse order, right parentheses. This takes us to an intermediate state, and that intermediate state then comes back here and says read epsilon off the input, read epsilon off the stack, and then push on a left parentheses.
What is the first transition?
This first transition is epsilon, Q, right? The second one is epsilon, epsilon, left. Now, we have one more, and I'll put it down here because everyone out of room up there. Again, ordering of these loops around here doesn't matter, it's just run out of room. Which represents this rule. Q goes to left parentheses, Q right parentheses. So here, we have one rule, read epsilon, read Q, push on right parentheses. We have another one here, which says read epsilon, push on Q. And then we come back to here with epsilon, right parentheses. Yes. Oh, it's dyslexia. Catch the fever. So that rule is that, and then we have another epsilon Q here. So for these rule states, you're always reading epsilon off of your input. The first one of them reads the variable that denotes the change. And then every intermediate step is pushing on in reverse order what's going on up there. Let's step through an example of this, and then I'll talk about why it works. That sound good? Okay. So, let's do left, 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 right, right, right. So that's our input. And then we have our stack over here. Okay. Start off in our start state. Only one transition to take. Push $sign onto the stack. Yoink. Now we're in this state. Only one transition to take. Push start onto the stack. Yoink. Now, remember, you can only be in the accept state if you were there. You're only accepting if you were there after having consumed all your letters. So because it's an NFA, in theory, what we could do is we could say, oh, we'll take this epsilon start epsilon transition, get rid of the S up there, then take the epsilon $sign epsilon, be in the queue accept. Yay, it looks like we win, but we don't. We don't actually win in this because we still have the entire input to process. So even though we found a way to get to there, we hadn't actually processed all of our input. So where do we go from here? Oh, we go to the fail state. It's like if you have a treasure hunt and you go all the way, you have to get all of the pieces to actually win. You can't just end up at the ending like, yeah, I won, I got to the finish line before anyone else. Like, yeah, but you didn't do anything. That's what's going on here, is you have to actually do something.
So you have to actually pop those parentheses into epsilon?
You don't have to pop them, but you have to be at the end of this. You have to have finished process. You have processed everything. So your pointer for the string here needs to be right after the input string. If you have not finished processing the input string, merely arriving at the accept state does not mean you have completed it. Arriving at it with no input means you've done it. Does that make sense? Sean, you got that? Okay. So, we're now in the queue loop state. We're looking at the first input. Well, what can we do? Again, we have this is a non-deterministic system. There's actually multiple options we could do. And this is where it becomes multiple options. One of them is we could be doing this epsilon start epsilon transition. Now, we just talked about how that's not going to help us. So we see a start on our input, and we see a left parentheses on our tape. So which transitions can we take at this point? Well, we can take epsilon start to epsilon. We can take epsilon start to Q, and that's really it. Note that we can't take this transition, left to left goes to epsilon, because we don't have a left on the stack. We do have a left on our input, but we don't have a left on our stack yet. So we'll take this transition. Epsilon start goes to Q. That pops S off and puts Q on. Now which transition do we take? Well, there's multiple transitions that we can take at this point. Again, we could take epsilon Q goes to left parentheses and push and do this loop right there, or we could do that loop right there. Which one of those will help us parcel the input?
The one on the bottom left.
Okay, that one's going to help because that's going to give us another Q variable. If this one's just going to terminate after one loop through it, So we actually wanted to go down this one. So we'll look down here, epsilon q right parentheses. Okay. So we say, okay, consume the q, push on a right parentheses off the stack. Now push on a q. Now push on a left parentheses. Now which transition can we take? No. That one is not open to us anymore because the top of our stack is a left parentheses. So fortunately, top of our stack is left parentheses. Top of our input, our current place in input is a left parentheses. So we have this input, left parentheses, epsilon. So what happens there is that moves where we are in the string by 1 and pops off that terminal. Now, Q on the top of the stack, which one do we do? Yeah, we do this bottom one again. So we follow that, and this will push on a right parentheses, Q, left parentheses. This is why we push them on in reverse order, because the last thing which gets pushed on represents the first thing that gets popped off. And we want to pop them off from left to right. And so that's why it's in reverse order. Okay, so now which transition do we take?
You'd add another parentheses with the Q.
No, we can't do that one yet.
No, the one we just did, one with that one.
This one?
Yeah.
Yeah. Because so we have a left parenthesis on top of the stack. So we have to do the one that has the left parenthesis on top of the stack, which is this one. And conveniently enough, that's also our input. So we advance our terminal by 1. We pop that off the stack. We're back here. Q's top of the stack. So we now follow, do we want to follow that one or that one?
We want to follow the top right.
You want to follow the top right one because now we're deep enough in there that we actually want this to be our last one. So we pop Q off the stack and follow this transition. Epsilon Q right parentheses, epsilon epsilon left parentheses. Now we come down here, left parentheses epsilon, yay! Advance that, pop that off. Right parentheses epsilon, yay! Right parentheses epsilon, yay! Right parentheses epsilon, yay! No more input. We're at the end. Hey, what's at the top of our stack? $sign. So, follow this transition, pop $sign off the stack. We have no more input, accept. Again, I want to stress, with PDAs, you have to have 0 input when you finish, but you can have contents left on the stack. We didn't actually have to pop up the $sign here, but it's generally considered good practice because you want everything to be empty when you're done. Does this make sense?
You can just leave pretty much everything in the stack at the end, or
But what? What?
No, I'm just trying to understand.
So the stack is traditionally, when you're creating PDAs, traditionally you want the stack to be empty. It need not be. The input must be empty at the end. But traditionally the stack is also empty.
Okay.
You don't have to. That's not a requirement. It just makes it easier to follow it.
So if you're building this, would you put the input in the stack?
No. The input lives on a separate. They're 2 separate sections of memory.
I mean, not the stack, but like a stack.
No. You would actually. It's actually a queue.
Oh.
I guess you could view it as a stack, but it's probably best viewed as a queue, because you're really doing it in the order that it occurs.
And it's also just checking to see if it's valid, right?
Right.
So once it moves from one to the next, it doesn't really.
It never goes back.
Yeah.
And that's one of the things which will differentiate this from a Turing machine. Is a Turing machine has ability to go back on the input. and validate things in the past. This doesn't. Once you've consumed input, it's gone.
So just to be absolutely certain, this is essentially the process of maneuvering to the point where you have the input character on the stack so you can pop it off, which then eliminates it from the input.
Right. And so what happens here is that each of these rules, these epsilon variable rules, pushes on the variable transitions. Notice that consuming a variable does not take anything off of there. It does not progress you in terms of there, and that makes sense because it's a variable, it's not a terminal, it doesn't actually appear anywhere. And so what you're trying to do here is you're trying to basically build up the parse tree on the stack, but you're only building up the parse tree that you actually care about. As soon as you got into a terminal, you're done with that. You've done your job, it's a terminal. You may not be able to parse it because it may not be in the correct order, but if it's a terminal on the top of the stack, that means we're good to go and we can move on to the next one. Because consider what would happen. The parse tree for this is start goes to Q. Q goes to left parentheses, Q, right parentheses. Hey, a left parentheses is there. We're done with that. That's not taking us any further. That left parentheses matches up with that one. Yay, let's check that off. And let's keep going down this Q, see how things go. All right. That Q goes to left parentheses, Q, right parentheses. Oh, look, another left parentheses there. Let's check that off. Move on to the next one. Oh, left parentheses, right parentheses. Oh, a left parentheses there. Let's check that off. Go to the next one. What, is there anything in the middle? Nope, no more variables down there. Oh, right parentheses. Hey, how convenient. Oh, we're doing good here. Oh, we're done. Yay. And so that's what's going on. It's simulating this process of, as you see them, you're just checking them off. I guess it's not simulating, it's doing that process. But you can't actually run this because it's an NFA. So you guys want to do a more complicated grammar?
Why isn't there a Q variable in the last one? Is it just...
Oh, because you don't want to keep on going forever. You only need 3 here. And so
that's just computer choice.
Yeah, it's the NFA, magic NFA, magic non-deterministic choice of, that's the best option for us. Non-determinism is great like that. It always chooses the best choice. You can view non-determinism not as necessarily choosing, as choosing all paths and just happening on the correct one. You can also view it as being with that really smart, annoying guy who always knows the best choice. And they're just always choosing, the machine is just saying like, oh, I just happen to know that's the choice I want to choose right now. And they always know the best choice to do. And that's another way of viewing non-determinism that makes it easier to understand. It is not everything happening all at once, which is not at all realizable. You can view it as just the smart ass always knowing what the best choice to make is. So that's another way of looking at it.
Wouldn't the best choice for everything be to stop being a smart ass?
No.
Oh, it's an interesting game.
No. You don't know enough smart asses that. That's never the right choice for a smart ass. Do you mind if I erase this so I have more room for the camera? So, smart ass actually do not get paid as well as they think they do. But they get to live their life feeling better than everyone else. Knowing deep down someday they will die. My class has been a real bummer ever since I started finding this funny. So what did you do in CS today? We learned about PDAs and were reminded of our own mortality. That's interesting and depressing. So let's do that other grammar we talked about yesterday, where we have A to the I, B to the J, C to the K, where I equals J or J equals K. So I'm going to write up the grammar for it very quickly. So, start goes to X or Y, and also for simplicity, I'm going to, again, assume I, J, and K are all greater than 0, because I don't want to have to deal with epsilons. So x can go to a, or it goes to AD. A goes to lowercase a, capital A, B, or AD. D goes to lowercase c, or C, D. Y goes to W, Q. W goes to A, or A, W. Q goes to B, C, or B, Q, C. When I'm writing this up by hand, a convention I like to do, terminals are always lowercase, variables are always uppercase. It makes life a little bit easier. Also because I don't write italics well. I don't have as nice a handwriting as the math department. I always so depressing when I go on the board and the math professors haven't erased it and it's so pretty and I'm like, I will never get there. I still remember clearly when I was in 5th grade and I wrote the first word that other people could read. Yeah. I could read it all fine. Anyways, so let's go and create these different states. So we have start. Start will push on. I wonder if there's another pen. The point on that one is really kind of dying. It's hard to write these precise epsilons. Oh no! Ugh. So epsilon goes to $. $sign here. Epsilon goes to a start variable. I'm going to draw my loop state really big here. And then that's going to eventually go to except is going to be epsilon, $, epsilon. So let's start off making the self loops for the terminals because that's the easiest one. Now, to save room, I'm only going to write one self loop and just label it with 3 different things. And that's a perfectly legitimate thing to do. So, A goes to epsilon, B goes to epsilon, C goes to epsilon. Now, I'm going to draw another loop. And this, I'm also going to label this with 2, and it's because they're both good with single state here. So I'm going to shortcut that a little bit as well, which is that we have epsilon start goes to X, epsilon start goes to Y. Now we start getting into the more interesting ones. We're now going to do XAD, so that's going to add 1 intermediate state there. And this first one is labeled epsilon X goes to D. And this second one is labeled epsilon goes to A. Make another one here that's now talking about A. You go epsilon A goes to B. Epsilon A. It's now talking about that rule. This one is, it's really hard to write upside down on the board. Epsilon A, oh, fiddle faddle. Epsilon A goes to B, epsilon goes to A, epsilon goes to lowercase a.
What is the second loop with the intermediate state? The one to the left, not that one. Oh, that the second like actual.
That one?
That one. What is?
Epsilon A goes to B, epsilon goes to A.
Lowercase a.
Lowercase a. It's talking about that rule. It's a nice process because it's largely mechanical once you get used to it. Now we're at this rule. This is actually the first one. This is easy. Self loop. Epsilon D goes to lowercase c. And then we have that rule, the second half of it. Epsilon D goes to D, epsilon goes to C. Now we're at this rule. Y goes to WQ. Epsilon Y goes to Q. Epsilon goes to W. Now we're at W goes to A. Epsilon W goes to little a. Now we're at epsilon W goes to W. Epsilon goes to lowercase a. Now we're at Q goes to BC. Epsilon Q goes to lowercase c, epsilon goes to b, and then finally we're at epsilon Q goes to c, epsilon goes to q, epsilon goes to lowercase b. Whew. And that's the PDA for it. You want to walk through it with an example? Seems like a reasonable idea. So, let's walk through A, B, C, C. God, I'm going to hate this so much. What?
So you said it's so much.
Well, there's examples like to do it interesting, it needs to be one needs to be different size, and one has to be 3, and one has to be 2. Okay. So let's draw our stack. Okay. Start off. No, I'm going to try and go through this quickly because we only have 8 minutes to go through this example. So tell me if I need to. Tell me. I'm going to stay over here and not point out the states we're following.
From the start to the next node is F1 assigned to the dollar sign. If it, and then the
Oh, you're right. There's a mistake in there. Yeah, I'll fix that. It should be epsilon $. Okay. I drew it correctly on the board and put it incorrectly on the slides. Oh, I did? Okay, cool. Thanks. Yeah. No, thanks. Yeah, this is the correct way of doing it. Epsilon $, epsilon. I should have taken a point off. -1.
From me?
No, from me. I lost a point. I lost a point.
arguing in class.
No.
Well,
Pointing out correct professor's ignorance, -1. No, that's an important mistake. I mean, it would have cost me a point, but it would have cost all of you a point. You'd be like, but you should have said to do it that way, and then I would feel like a jackass. But if everyone had missed it, I probably would have given people a 1-point curve. But Hong would have gotten it right, so then you all would have been screwed by that. So you shouldn't have said anything.
Now we've only got 5
I'm
minutes.
just waiting.
Yes. No. Okay. Let's go through this.
Group breaker.
Okay. Epsilon $sign epsilon. Okay. $sign on there. S goes on there. Okay. Now we're on here. Which transition do we want to take? Well, we're going to have a matching number of A's and B's, so I know using my power of foresight that I want to replace S and replace it with X. So I'm going to take that transition. X gets popped off, and I'm going to replace it with D and A. A, I'm going to want to, I'm going to need to go down it 3 times because I have 3 A's that are matching. So the A will initially get replaced with B, A, A. I pop off the A because I use a self loop to remove the terminal. Then I'm at an A again. Oh, which transition do I take? The one that goes to AAB. I take that, put another B on there, put the uppercase A. Stack's going to have to go wonky. Put a lowercase a on there. A is a terminal. That means I can just remove it from there, progress my input by 1. Now I have A, B, B. I'm at the A transition. I want to now put my final AB on there. So I'll take the transition AB, which is right there. B, A. Now I have my A transition. I can remove that it's a terminal. I can remove the B, it's a terminal. I can remove the B, it's a terminal. Remove the B, it's a terminal. My string input is currently pointed there. So for each one of those terminals has advanced me 1 in the input. I'm at D. I know I have 2 levels of C, so I'm going to want to take the transition. This one here, which keeps the variable. So I put on there, I pop the D off and then immediately replace it with a D. And Zeno mentioned before, you can actually do that where you pop it off and replace it with the same thing. It's perfectly legitimate. I now put a C on there. C is a terminal. I remove it. D is on there. Well, this D is going to be the last C, so I'll use that transition and replace it with a lowercase c. I'm now at that point in there. C is a terminal, so I can remove it. Advance my pointer to the end of the string. I'm done with the string. I have nothing on there. I have a $sign on the stack. I remove the $sign off, go to the accept. I'm done. Woo! Yeah, it's 1 minute. Yeah.
Wasn't that painful?
Yeah. All I had to do was speed talk. So does this make sense? Do you guys have any questions about this process of why it works, or? Does it make sense at a high level of why it works?
Yes.
Okay.
I just don't want to code it.
All right. You don't have to. You can't code this. You can't. It's impossible to code this.
I actually like this almost better than the DFS.
Mhm.
Because it's, I mean, like, you said earlier, it's more mechanical.
Yeah.
You get
It's
to
like a
follow
real
the
process.
Yeah.
Yeah.
I feel like this makes no sense. Yeah. You see us doing 4 yesterday. I had fun forgetting to go back to 1.
This one is easier. The difficulty with the DFA is it's very easy to get lost at some point in that process. Here, it's much easier because it's much easier to keep on track because ultimately there's fewer states of what's going on. I mean, you can count up your rules 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then count up these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yay! I have the correct number of rules. That part is going there. Do I have 1 for each terminal? Yep. All right. Probably doing well. The biggest mistake people make is not putting them on backwards. Put them on backwards. That's the hardest part about doing this and keeping them correctly. Is people will often when you're on the test, you'll see this and you'll write, oh, the transition should push A on first, then big A second, and then big A third, little b third, as opposed to pushing them on in reverse order. That's the most common mistake I see people make with this. But NFAs and DFAs, there's so many steps in there that it's so easy to get lost in one of them that you make a small mistake in one and that can have repercussions all down the line, which doesn't really bother so much for you unless you're a perfectionist, because I'll just take off 1 point for that mistake, and then I have to rederive it from your work, which is why I despise grading those problems. I make you do them despite the fact they're my least favorite thing to grade. So, because everyone makes one mistake. And it's a different one. You all can't be consistent, conspire about, we're all going to make this. That'd be odd if you all make the same mistake. And I'd be concerned about that. It would make my life a lot easier. We all decide we're going to get together and make this one mistake. You just leave a note on there, Aaron, we all decide this was a mistake we're going to make. Yeah. We collectively decided beforehand, without doing the assignments, we were going to make this specific mistake. And then we all went separately and all made that mistake because that was what we agreed upon. No cheating was involved.
Except for Robert Ryder, he made no mistake.
Yeah, he made no mistake. He didn't. Yeah. Any questions about this? No, it's very funny.